I got this crazy idea from anonymous source for how to do inputs to large language models. First of all, digital world is in bytes, so we want to put bytes directly into large language models and other AIs and not tokenize it. Bytes are lowest common denominator, and that will help us maybe merge all of these modalities, text, video, image, in the best way. And this is so interesting. We can learn patterns about bytes, how bytes are positioned. For example, if we have text and we split 4 bytes and then 4 bytes, just move by 1 byte and split it to these 4 bytes groups, the text. And then each of the 4 bytes is like a dot in a 4-dimensional space, because the bytes are from 0 to 255. So those are coordinates. So each has window has 4 coordinates, each dot has 4 coordinates, the 4 bytes. We can then use topology analysis. So we take a byte, a dot, we grow sphere around it, around each of the dots of the text, spheres. And then we look when they start to overlap, when they form voids, when they don't overlap. If the spheres don't overlap, it means there is some forbidden text combinations there. So we can learn about bytes, about text more, and how we can structure them, how we can put them. We can learn rules about bytes, how they're gonna exist, so we design better LLMs and visual language models and all of the other AIs. So AI will be able to learn most, and it will be able to generate bytes directly without any conversions. And it will be then a lot more expressive and better and more understanding of everything. And we'll be able to fully understand entire digital world. So in my previous series of 4 videos that you can check on playlists, I tried to replace tokens with bytes, but I did it in, maybe the person said, in a naive way, where I just tried to group a few bytes based on how difficult the next byte is to predict. So I group, if it's difficult, then I just group a few bytes. If it's easy, then I group more bytes and then process that patch as a token. So then the person said that gave this idea of using algebraic topology to analyze bytes. I have no idea about algebraic topology, so let's learn from GPT-5 and Claude Opus and learn about this idea, because I never really did algebraic topology. So we will explore together. Imagine you are looking at a constellation of stars in the night sky. As your eyes adjust, you start connecting nearby stars to form patterns. Triangles, loops, and more complex shapes. Nice, okay, I understand. Persistent homology, which is what the person told me to use to analyze bytes, is like systematically doing this at every possible connection distance and tracking which patterns persist across many scales. Okay. So stars, we're trying different connections. We're trying to connect, I guess, every star to every star and see which patterns persist with many scales, many different distances. For byte sequences, think of each byte position as a star in a high dimensional space. So it's a star in a high dimensional space. It's like a dot, it's like a vector maybe in a high dimensional space. We want to discover the shape of how these bytes relate to each other. Okay, let's go. Okay, math will help us solve this problem. Are there loops, clusters, voids? These topological features can reveal structures that linear sequence models can miss. So are we gonna create new type of neural network, or are we gonna analyze this in a different way? I'm not sure. But what does it mean by linear sequence? I guess our neural network will also be high dimension, not just 2-dimension. We got a formal math explanation here. It's a bit tough to understand. So now Claude Opus generated all of this code. We're gonna use this to analyze these bytes with this topology thing. We got a bunch of images that we will figure out and analysis. So we have this sentence: the quick brown fox jumps over a lazy dog. And we have these bytes, converted this sentence to bytes. So we just print 50 characters and we print 20 bytes just for preview. But we have this sentence 3 times. So this tutorial explains how we apply topological data analysis to analyze byte sequences. revealing hidden geometric structures that traditional sequential processing might miss. I just copied the output to Claude Opus and told it to explain. It has its own code as well and everything. Think of it like creating a shape from your data and studying its properties. For example, loops in the data, which we have 3 of the same sentences, those are these holes in the topological analysis. Not sure what those are though. Connected components are clusters and voids higher dimensional cavities. So we will understand what these are. But these whole connected components and voids are what happens in the topological analysis. So besides this quick brown fox sentence, we also have repetitive pattern. We generated this data as well, where we just have these 3 bytes ascending in order 65, 6, 7, 8 and repeating them. We also have random data, random bytes, completely random. So that's gonna represent like a noise. So this repetitive would be like compressed or structured data. And then this text in the beginning would be real world text data. Then we have data with a header. So it has a header and then it has some other data. So this is like a JPEG header and content that we could process in like our vision language model. And that's file format simulation data. So I must say these LLMs are actually so helpful. Imagine I didn't have this, I wouldn't understand I wouldn't know any of this. And then we have a gradient, which is gonna show us smooth sine wave. Smooth sine wave pattern, continuous transitions. It has continuous topological features. So the repetitive one should create loops in topology. I'm also hearing about this for the first time, but I think I can follow a little bit, yeah. Random has no structure, so we expect minimal persistent features. So features should not persist or even exist. And then structured with mixed patterns, we should be able to understand what header is and what content is. Okay, let's see basic byte analysis. Before topology, we computed traditional statistics. Text sample analysis, so length 135 bytes, unique bytes 29 out of 256 possible unique bytes. Entropy 4.4 bits, 4.44 bits, measures randomness. So I guess randomness of the next byte. Or no, maybe randomness of the whole sequence. Maybe if there was more unique bytes, then entropy would be higher as well. So high entropy would be that data or bytes look very random. So maybe text would be very random letters as opposed to this where we have, like, for example, more letters A and more of these letters, less of these letters. But in random, it would be so very random and high entropy. Autocorrelation 0.26, that means low repetition. So if it was 0.92, for example, it will be very repetitive. Strong self-similarity. 0.98, they say gradient, smooth transitions, interesting. And then I'm not sure 100%, but 0.20 is no pattern. So I guess these are examples. We use 3 embedding methods to convert byte sequences into geometric spaces. First is sliding window embedding. So byte 1, byte 2, 3, 4 into a single window, then bytes 2, 3, 4, 5 into a single window, etc. Creates overlapping windows of bytes. Shape is 132 and 4 means 132 windows of 4 bytes each. Good for local pattern detection. Then we have this delay embedding, so you take every second byte, for example. So byte at byte at I plus 2, I plus 4, etc. So if the final shape is 129 and 4, it means we have 129 points in 4D shape, which is, this is just a tensor, you know this, if you do machine learning. This is good for detecting periodic patterns, interesting. And then frequency embedding, for each byte position, count byte frequencies in local neighborhood. Create 32-dimensional frequency vector. Okay, what does this mean? Okay, we have 32 dimensions and we have 135 of those vectors, or those are positions, with 32 frequency bins. Good for statistical patterns. I'm just not sure how this is created, these 30, how they are selected. We'll see later. Distance matrices. After embedding, we compute distances between all pairs of points. So text sample distances, Hamming distance 0.952 average, very different windows. Okay, we have Euclidean distance and frequency distance. I'm not sure what they mean. Key insight, repetitive pattern shows distance equals 0 in frequency embedding because all local windows have identical byte distributions. Okay, so if the pattern is repetitive, then distance is 0 in frequency embedding because all local windows have identical byte distribution. I guess they are same bytes, so distance is in every window, so distance is 0. Computing persistent homology. This is where magic happens. We build a filtration. Imagine connecting points at increasing distances. So this is going to be a bit difficult, so I told it to explain it in even easier way. Let's start with a simple analogy. Imagine you have a connect the dots puzzle. So this is the puzzle, connect the dots puzzle. But you don't know which dots to connect. Persistent homology is like gradually connecting dots that are close together and watching what shapes appear and disappear as you add more connections. Step 1, understanding points in space. Your bytes become points. When we converted bytes to embeddings, we turned each position into a point in space. This is so interesting. So we just group bytes and then they immediately become points in space. That's crazy. Those are dimensions, X dimension, Y dimension, Z dimension, and there is a lot more dimensions in this coordinate system, imaginary. So we got original bytes, and after embedding, we group them, let's say this in these windows. So first window takes first from first to fourth, and then from second to fifth, from third to sixth, so it's sliding window. Now imagine these points floating in space. Some are closer together, some are far apart. Cloud Opus is the best AI, it's explaining so well. The growing ball analogy. Here is the core idea. Imagine each point has an invisible ball around it that grows over time. That's crazy. So time 0, tiny balls, nothing touches. Time 5, balls growing, still separate. Time 10, some balls touch. We connect them. So we connected them by time. I mean, they connected themselves is what I understand. Time 20, more connections form. And time 30, triangle. How? 3 connected points form a loop. Maybe something like this. Maybe they somehow grow and connect like this. I'm not sure. Maybe there is 3 of them. So this one connects as well. I'm not sure. So we just understand the 3 connected balls. They are connected and there is like triangle in between them. Maybe triangle sides are like this, like curved like balls or spheres. The radius of the balls, the filtration parameter epsilon. So there is this filtration parameter. Step 3. What we're actually looking for. 3 types of features. Dimension 0, connected components. Think separate groups. So, okay. Early, when epsilon is small, diameter is small, then there is 5 separate groups, 5 separate dots or spheres. Later, maybe one connected group, and whatever other groups are separate, how many? Maybe 3. And what happened? 4 groups died as they merged into one. Okay. So 4 group. I mean, like one connected group of all of the spheres, and it was 5 separate groups in the beginning. Dimension 1, loops. Think circles, cycles. 3 points A, B, C. Connect close ones. So I guess it connected A and C and B and C. No loop yet. connect all. Not sure what, but okay, so now I guess all are connected and there is a loop. Dimension 2, voids, think hollow spaces, like a hollow sphere or bubble, rare in byte data, needs many points. Understanding birth and death. This is the key concept that confused you. Every feature has a life cycle. Birth, when the feature first appears. Death, when a feature disappears. Fills in or merges. So the separate groups, they merged into a single group, so the separate groups died. Persistence is death minus birth, how long it lived. Real example from your text data, dimension 0, 44 features, max persistence, 69.325. This is what it's talking about, computing persistent homology. And here in text, in the first example, we have 44 features, max persistence 69 seconds. No, it's not seconds. What is this? 69. This means 44 separate groups of similar byte windows were found. The strongest group survived for 69.325 units of distance. Okay. The group was born at distance 0 and died merged at distance 69.325. Maybe this was a window, these 4 points, that was furthest away from every other window. Let's trace one specific feature. So we have the quick brown fox, we have those 4 words. At distance 0, they're not expanding, they're not growing, they're spheres around them, wherever those points are. So at distance 0, we have 4 separate groups. Distance 10, brown and fox can merge because they're close together, and when they grow, they're spheres, then those spheres can merge. Distance 30, we have the quick and brown fox. And distance 69, the quick brown fox, all merged into one. Feature brown fox group. So let's say this group brown fox. Birth distance 10 when brown and fox first connected. Death distance 69 when it merged with one with the quick. So persistence is 69 minus 10, which is 59. Live for 59 distance units. This is just an example here. So in our data we got maximum persistence out of all of this for 69. I'm still not sure what this dimension 0 is and what this 44 features is. Step 5, let's decode your actual results. Bro, Opus is reading my brain. Oh my god, it's crazy. So what does this actually mean that I just asked? Dimension 0, connected components. Dimension 1 is loops. And dimension 2 would be those voids that we don't have. So we have dimension 0 and dimension 1. And dimension 0 has 44 features. Connected components. So those are just 2 connected components, but there is no like 3 or more where they form loops. So I'm imagining this as each dot grows a sphere, and in dimension 0 we just have 2 spheres and maybe more spheres connected, but there is no loop between them. Dimension 0 started with 129 points, 1 per byte window. What is byte window? As we grew the balls, points started merging. Okay, so I guess we got 129 windows. I understand. So each window has 4 bytes, and we can take those 4 bytes as dimensions, so place in a space. So it's a dot in a space with 4 coordinates, that one window. And there is 129 windows, so 129 dots in space. As we grew the balls, points started merging. 44 mergers happened at significantly different distances. The longest lasting separate group survived 69.325 distance unit before merging. Interesting. 44 merges happened, so some were close dots merged, some were long dots, far away dots merging. So that we have 44 of those. And this is this is so crazy. Who invented this, bro? And then dimension 1 loops. 11 loops formed in your text data. These represent cyclic patterns in your byte sequences. Example, the phrase "the" appears multiple times, creating a loop when we connect similar windows. The strongest loop persisted for 21.668 distance units. So it is a bit confusing. The way I understand it is we have word "the", so there are some same bytes. There will be some maybe same points even. So same bytes, same points, maybe points would overlap, and then when they grow they are all close together, maybe because we have multiple times word "the", so they can have 3 same coordinates or 4 same coordinates, so they will be close, and then when their spheres grow, because they're stacked up together, they can form loops. So Opus says we're almost understanding it. You're right about the similar coordinates, but there is a subtle twist about how loops actually form. When "the" appears multiple times, those byte windows will indeed have similar coordinates and will connect early when both are small. Because we have same word "the", it has same bytes, so windows of 4 bytes will get same bytes or similar bytes, maybe 3 same bytes, which means 3 same coordinates, which means they are close, very close. The subtle part, how loops actually form. A loop doesn't form just from multiple copies of "the" connecting to each other. Let me show you. Scenario 1, multiple "the". No loop, just a cluster. So we have text "the cat", "the dog", "the". Windows containing "the" would be the cat, the dog, and the end here. Okay, this is a bit confusing. Okay, let's just say we have 3 points. They have this "the". When balls grow, let's say A and B connect and A and C connect. This is not a loop. It's just a cluster, connected components. Because B and C are not connected in this case, all 3 "the" points connected, but they form a tree, not cycle. Scenario 2, how a real loop forms. Text, the quick brown fox jumps over the lazy dog. Byte windows simplified. So point 1, the quick coordinates. We have these coordinates, let's say 6 bytes for the first letters. Then we have this window, it's starting from here. Okay, we have these windows, let's say. Here is the key. Loops form through different paths. So maybe this part that has the QU can connect to this the LA, and then this also can connect to these 2, but there is no loop. This is a distance 10. Distance 20 more connections, so this connect quick to this one here. Now we have a loop. You can trace a cycle through the connections. Okay. The critical insight, it's about pathways, not just similarity. Why "the" appearing multiple times helps create loops. Multiple "the" instances act as hubs that connect to many other windows. Yeah, because they are similar close coordinates. These hubs create multiple pathways between points. When you have multiple pathways between points, you get loops. The way I understand it is if they have both they are more likely to connect to each other because they're close, and they will anyways have other connections, so then there is higher chance that a loop will form there. You see here, the thing is "the" can connect to other things, but they're also likely to connect to themselves, so they're likely to create this additional pathway that connects them. So they created 2 loops here. Because in the beginning, without "the", we had A connects to B, B connects to C, D, E. But then we have "the" connects to A and C. And then "the" connects to B and D. So it creates these two, and then the connects to itself as well, because it's, I guess, close. And since we have multiple paths from A to D, we have a loop. Path 1 is A, the, C, D, and path 2 is A, B, the, D. So I think we got it. Similar letters or same letters means similar coordinates, which means because similar bytes. So it has small distance and connects early. So when we have these, let me break this down with concrete examples. Identical windows equals identical coordinates. The and the have same bytes, distance 0, they are the same point. Let's say we have the space and the dot, just dot would be different byte. So it only differs in one byte, one coordinate. Euclidean distance between space and dot is 14. They connect when ball radius is 14. And if we have different windows, we have faraway coordinates. Now their Euclidean distance of these two different is gonna be 27. They connect when ball radius is 27.3, much later. This is opus being a bit confusing because there is 27 distance between the points, but I guess when the spheres grow, they will connect halfway. They doesn't need to grow this much. But I'm not sure which one is correct. Okay, well, we'll figure it out. So it said that it corrected itself. Each point has its own ball growing, and they connect when the balls touch. So this is the correct picture. It says distance between points 20. So GPT-5 also said that they join when the two growing balls first overlap, so halfway through. This happens when the ball's radius reaches half the distance between the points. So then this is correct explanation. So distance between points, let's say 20. At radius 10 for each ball, we have the following. Radius 10, it's gonna touch because both of the balls have radius 10, so they connected. So if the distance between the space and the dot is 14, then each ball needs to grow to radius 7, and we have the and xyz exclamation mark. Then distance 27.3, and we need to grow the ball to 13.65. And this creates your persistence diagram. So at epsilon 0, all identical windows connect. Clusters of the, where it's just the. Epsilon 5, very similar windows connect. Epsilon 10, similar patterns start to connect. Some loops are born here. And then more loops are born. And then at some point, the last persistent loop finally dies. Some connections fill it in. At epsilon 30, most things connected. At epsilon infinity, everything connected, one big blob. This is interesting. In my random bytes, it creates more topology features than structured data. So we got 122 vertices or points. These are windows. We have dimension 121 features, connected components with maximum persistence 117 unit lengths. So what that means is we have 121 connections between these different points when they grow. So reminder, dimension 0 shows connected components, so separate blobs where there is no loops. It's just few spheres or connected. So at the starting point, every point is separate. So every point is its own connected component. As these spheres around them grow, as epsilon increases the radius, then some points start to merge, some spheres. You can even have 3 or more spheres merge, but it's not a loop because there is no multiple paths from one point to the other. Now we have fewer components, maybe 80 instead of 122, because some of them merge into a single component. And eventually you have one giant connected component if sphere is reaching infinite. radius. So somewhere in that margin, let's say when epsilon is 20, there can be a loop born. So important thing, and when we are counting loops, we are just counting independent loops when there is no connections in between. So here we actually just have two loops, two independent loops, this loop on left and this loop on the right. So we don't count this big loop, and if there was connection between B and F, then this would break this loop. So we want to see holes as well. We don't want anything inside of the loop. We don't want connections inside of the loop, because then that loop around would be combined of the two loops inside. So we don't want these dependent loops, only independent loops that are not combined from other loops. And if you have two diagonals here, then this would completely destroy this loop, that hole, because there would be no loops inside. Both of the loops that are formed with one diagonal would get cut by the other diagonal, so it would just there would be no holes anymore. We only want loops that they have no connections inside. So in our random data example, we might have thousands of possible cycles, but we only want to track independent holes in the space where that are not formed from smaller loops, just independent holes, that there is no connection inside of them. Homology tracks the basis minimum set that generates all others. And keep in mind, when everything is connected, there is fewer holes, because all of the loops now have connections going through them. But so there is no holes. And then this dimension 1 that we measure, this is how many of these holes in total there are during the entire process. So some will be born, some will die later, but in total. In the end, there will be 0, because all of them will get crossed by different connections. And the longest living one lived for 37 units of expansion of radius. So as radius grows, we're gonna have more loops, but then there is a peak, and then they start getting crossed by different connections, and then we go back to 0 loops. Then dimension 2 is when you have some space that's completely encapsulated by some 2D shape. So like a ball, and there is empty air inside of the ball, but that air is completely encapsulated by the ball. So that's the dimension 2, voids or cavities. And in this case, there should be nothing inside, like no other dots. So then that would be considered as this void. We have 14 in total of those in our random example. So as these spheres grow around these points, they can all connect around, so it's empty inside. But as soon as 2 points like B and D connect across the middle, then that's gonna cut this void, and there is no more void, the void dies. Because now the void is cut in half. So now we can have maybe 2 voids, but this one, big one, died. Because these 2 voids are no longer separated. There is no air, there is no space in between, they're completely separated by this new connection. So what this means, if we have some structured data like text, and we see one void, there is probably meaningful structure here where we can learn something from this. But if we have a bunch of voids from random data, then there is nothing to look for. Because it's random data, there is no meaningful interpretation or structure, just topological noise, and it's accidental. I said earlier that voids can be split into 2, but it says here that it's difficult the higher dimensions you go. So in 3D, adding one edge through void kills it. Adding a surface through void might split it. In dimension 4 plus, need even more complex structures to split. Single connection almost always kills. So I asked, what would a void in text data mean? Geometrically, a void means byte patterns form a shell structure. They connect in a surface that surrounds an empty region in the embedding space. So, byte windows that are similar enough to connect to neighbors but arranged so they surround forbidden territory. No byte patterns exist in the middle. What would create a void? Scenario 1, grammatical structure. So we have text, the cat and the dog and the bird and the fish. Byte patterns cycle through, so we have 5 bytes, the x, x and the y, y and, so this cycle. In embedding space, they can connect to each other, this similar, so the cat, cat and the. So they form a shell around, but there is no connection between cat and dog, for example. So the dog, dog and, so this is one void, this is the other void, but there is no connection between these opposite ones. The void represents absence of certain word combinations in this scenario 1. Scenario 2, structured format like JSON. We have name Alice, age 30, city New York City. So here absent patterns would be 30 NYC and Alice and 30 together. So those could be creating voids. The structure forbids certain byte combinations, creates void in embedding space. Okay, so now we come to the point, how can we use this to input bytes into transformer, into LLM? I still don't know. Maybe we can ask this guy. Why text has few voids versus random bytes? Because natural language uses many transitions, few forbidden combinations, patterns fill space more uniformly. But if we have random bytes, then these voids can be created randomly. And our one void in text that we have, it lasts for very short distance. This might represent punctuation boundaries. So sentence dot the here, so that's the common, but no space between never happens, no dot never happens, equals small void around missing space patterns. So these patterns that never happen, like without space and without dot, there is small void there. This is the most interesting thing I've ever seen. So we can predict forbidden combinations of bytes or forbidden text just by these voids. For example, in JPEG, in text, in PDF. That's crazy. I think I will end this episode here, and I'm gonna create episode 2 as well, continuing to explore this. So see you next time. Check the playlist for this series below. I'm gonna link to the second episode as well in that playlist.